Okay, so that concluded section 3.3 rules of logarithms, and now we're ready to begin section 6.4 system of equations in two variables. Okay, it's fairly straightforward. So in example 1, we want to verify that the ordered pair 1, 3 is a solution. So in order for it to be a solution, when we plug it into either equation, it should work. So we say 1 plus 3 is 4, and then 3 times 1 minus 3 is 0. So it checks out in both equations. So that means this ordered pair is the solution of this system. So then in example 2, we want to solve this system of equations graphically. So if we're going to solve it graphically, just go like this, and like this. So then I go 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Okay. It's a positive x, it's a positive y. So we're just going to graph each of these. So the first one I'll do in blue. So if we have x plus y equals 2, if we solve for y, then y is going to be a negative x plus 2. So I start at 2 here, then I can go down 1 and right 1, and I'll get this line here. Okay. So that's the blue one. And then the other one, if I have 4x plus y equals a negative 1, solve for y, then y is going to be 4x minus 1. So if we graph this, sorry, negative 4x minus 1. So we go down 1 is here, and then down 1, 2, 3, 4, and right 1 is here. So then we connect. Okay, we get a graph such. Okay. So if we're talking about the solution of the system, where do you think that occurs? In this example, it's going to occur here where they intersect, and they intersect at negative 1, 3. So we're saying that this is the solution of the system, so we can verify it. So when we plug it into the first, negative 1 plus 3 is 2, negative 4 plus 3 is negative 1. So the solution of a system is where our two lines intersect. So if a system has at least one solution, as in example 2, the system is consistent. A system with no solution we call the inconsistent, and the solution set is the empty set. A system of two linear equations and two variables must have one of the following types of solutions. Either one solution, which means the lines intersect, as you see in the graph. The system is inconsistent. System is inconsistent in the equations of one system, one solution means the line intersects and the system is consistent, and the equations in the system are said to be independent. No solution means the lines are parallel, as in part B, and the system is inconsistent. And then infinitely many solutions, which means the lines coincide and the system is consistent, and the equations in the system are said to be dependent. So then in this example 3, we want to just solve the system. It says by the substitution method. So if we're going to do substitution, we solve for one variable in one equation, and then we plug it into the other. So like in the first one, if we solve for y, then y is going to be a negative x plus 4. So then we take this and plug it into the other equation. So then we'll say x minus our y, which is negative x plus 4, equals 2. So then we can distribute our negative. So the negative goes in like that. So then we'll have x plus x minus 4 equals 2. 2x minus 4 equals 2. 2x equals 6. So then x equals 3. So then if x is 3, we can go and find our y. So then y is going to be negative 3 plus 4 is going to be 1. So we're saying that the solution should be 3, 1. And if we look at it, So 3 plus 1 is 4, and 3 minus 1 is 2. Okay, so that checks out. Makes sense. So now if we get a line such as 0 equals k, where k is some non-zero number, then the system is inconsistent. Let's see this in an example. So it just says solve the system of equations. I'm going to go ahead and introduce another technique that we have called the elimination method. So with the elimination method, we want to get one of the variables to be the exact same, only different signs. So I'm going to eliminate x, for instance. So what I can do is multiply that first row by a -2 and distribute. Now when I do that, it'll give me -2x minus 2y equals a -6, and then we bring down the other. Okay, I'll continue over here. Now if we add these two equations together, we'll get 0 on the left and 3 on the right. This is false. So because this is false, that means that the system is inconsistent and the solution set is the empty set. Nothing is going to work in this case. So in the last example, we got down to a line where we had 0 equals some number. It's also possible to end up with an equation that is equivalent to the equation where we have 0 equal to 0. The equations are said to be dependent and the system has infinitely many solutions. So we're going to use the elimination method again, and this time instead of getting rid of x, I'll get rid of y. And what I'll do is I'll multiply this first row by 2. So now my y's ultimately will be the exact same and only different in sign. So now I'll have -4x plus 2y equals -6. And then if we bring down the other part, when I add the two equations together, I get 0 equals 0. This is true. This is true. 0 does equal itself. So because this is true, that means that there are infinitely many solutions that are going to take on the form. So if we solve for y from one of the equations, so if we solve for y, like from that first one, we get that y equals 2x minus 3. So that means every ordered pair in the solutions for this system is going to take on the form x, comma, 2x minus 3. So for instance, like x can be any real number. Choose your favorite number. I'll choose 1. So when x is 1, then we see that y is going to be -1. So then the ordered pair that will work will be 1, comma, -1. So then we'll have -2 minus 1 is 3. 4 plus 2 is 6. So yeah, that was just one example. You can choose any real number for x, find the corresponding y, and you'll have infinitely many solutions there.